So today's talk is going to be about Lua and the way we use it in the engine, our implementation of it. And Lua is our scripting language. It's the most common way that people build gameplay in the Lua, though there are other ways, such as Flow or doing it directly in a C plugin. But Lua is definitely the most common way. So one of the first questions you could ask with our use of Lua is why we would use a scripting language at all. Can't we just use C++? Why do we need to introduce an extra language? Because of course introducing an extra language adds complexity. It's more to learn for the people who use the engine and so on. So there are a number of reasons why we choose to add a scripting language to the engine. First, it doesn't require source access in order to extend the engine with new code and write script new behaviors. That's kind of fixed right now, since for C as well, since we now have the plugin system, and you can actually write gameplay code in C and generate DLLs without needing source access, at least on Windows. But we didn't used to have that, so Lua was the only way to write dynamic behavior without source access to the engine. And of course, with for other platforms and Windows, Lua is still the only way to get dynamic behavior without source access. So another advantage is that you don't have to compile it for every platform. If you would do the gameplay features in C, you would have to compile it for each and every platform that we support, iOS and Android and Xbox and PS4 and whatever you needed for your projects, which can be kind of painful, especially since it requires you to have a full compiler chain installed for all those platforms. And that becomes kind of complicated. For example, to compile for iOS, you need OS X. So then you need a separate machine, like an Apple machine, in order to do that, because a lot of other platforms can only be compiled on Windows. So being forced to compile for being forced to have a compiler for every platform is kind of a pain. So it's nice to not have to do that. Another advantage is that with scripting code, we can put the code as a part of the project. So the code belongs to the project, which is appropriate for gameplay code because it's specific to each project. Whereas if you wrote it in C, the code would be more part of the engine. Not necessarily if you do it with DLLs, you could put the DLLs with the project, but it still would be loaded as part of the engine. So it gets a bit more messy. It's a bit cleaner to have it as part of the project. You get crash safety. You get a safety layer from the sort of sandboxing that scripting languages provide. So even if you mess up in Lua, you won't bring down the entire game, hopefully. Instead, you can sort of recover from that situation and proceed and use whatever tools you have in order to figure out what went wrong. So not constantly crashing is certainly a nice feature, especially if you have gameplay programmers who are better at gameplay than programming, which is often a thing that you want from your gameplay programmers. Often the people who have great talents in creating gameplay are not necessarily hardcore programmers. Another safety feature is that you get safety against memory leaks, kind of, since you have garbage collection. So that will eventually free stuff for you. You don't have to keep track of pointers and manually free stuff. Of course, it's not 100% guaranteed, because you can still have lingering references. Depending on how you set up your objects, you might have lingering references in some table somewhere that prevents everything from being garbage collected. So it's not a total protection against memory leaks, but but at least it protects you from some memory leaks and is easier to use than manual memory manipulation that you get in C. Another really useful feature, which is less obvious, is that you get sort of sandboxing, not only in terms of crash and memory leaks protection, but you could also get sort of a sandboxing of the abstraction layer. So with the API that we offer to Lua, we have sort of abstracted part of the engine into a separate API that you can use just to build the gameplay, and you can't really access any other parts of the engine. Whereas if you write your code directly in C or C++, directly against the engine, there is always a temptation to go beyond what the gameplay interfaces offer, and of course that can be useful because you can access more deeper parts of the engine and do stuff that you might not be able to do with the abstract API. On the other hand, when you start to do that, often you start to get leaky abstractions, you start to get modifications in the engine code based on what the game wants to do, and core engine concepts leak into the game, so that if the engine is updated later or sort of improved, your concepts, your changes won't merge nicely anymore, and everything might break down. This is again less of an issue if you use the DLL interface, since we have an abstraction layer there too that sort of protects the engine. But yeah, the main point here is it's really useful to have this layer of abstraction between the engine and the gameplay, so that we can modify the engine without risk ruining the gameplay and vice versa. And having the gameplay layer in a completely different language is sort of the highest level of abstraction that you can get, which is nice. We get hot reloading, so we can reload the Lua code without restarting the engine, which is nice. We can do that with DLLs too. So, but still a useful feature. You could argue that Lua is more expressive than C, and by being more expressive, I kind of mean that you can get more stuff done with fewer lines. You have to write less in order to do this, in order to do the same thing than you would have to do in C. This is maybe a point of contention. I think some people might say that, well, this is just because you don't do the right abstractions in C. If you do the right abstractions in C, you can get the same expressive power as with a scripting language. So this could be argued both ways, but I think a lot of people would consider scripting or higher level languages to be more expressive in general. You could also argue that scripting languages are kind of better for vague tasks, and by vague tasks I mean tasks that tend to change frequently, and where you're sort of more experimenting and are not exactly sure what you are doing. This is especially if you compare to like traditional object-oriented programming, like the way it's sometimes thought, where you start by drawing out your complete model, and you create inheritances and draw relationships diagrams between different classes and so on. That kind of design tends to create a pretty rigid structure for your project, and might not be that amenable to change later. And while as scripting language, which has sort of a looser coupling, a looser style of programming, might be better for vague tasks and things that require a lot of changes. This is again a point of contention. You could state, which I think is valid, that this is mainly because of the way you program in C++. Like if you make these heavy object models and like heavy create lots of coupling with dependency and inheritance. You get these rigid structures that are hard to modify later. But you could program in a different style in C or C++ if you wanted to, and get sort of the same flexibility as you get in a scripting language. So this could be argued both ways as well. But Lua is usually, scripting languages are more hackable than C. And by hackable, I mean that you can, since everything lives in a runtime, you can sort of modify things in ways that you're not usually able to do in C. For example, all the functions in Lua, even the functions that are implemented by the engine, such as the function for spawning a unit, is just stored in some global table somewhere. And anywhere in your Lua code or from the console, you can change that function to do something else. So if you want to, for example, if you want to log all the spawn unit calls, you could save the old spawn unit function in some variable, call it old spawn unit world spawn unit, and then you could create a new spawn unit function and store it and do some logging here, and then call the old spawn unit function and do something and spawn the unit as before. So it's kind of nice that you can interactively sort of change the behavior and dig into, get logs of all the functions that are being called and stuff like that. You could do the same stuff in C, maybe if you have a DLL and you have fast recompiles, and maybe you store all your function pointers in a table somewhere so that you can do hot patching or whatever. It's possible to do similar stuff in C as well, but it doesn't lend itself to that style of programming in the same way as a scripting language does. So these are all reasons why we wanted to have a scripting language in the engine, and why we choose Lua for the scripting language was also a number of reasons that made us choose Lua rather than any other language. To begin with, it's different enough from C to make it worth adding a new language. If we're going to add another language into the mix, we don't want it to be similar to C. We want to really have all these features that make a different kind of programming possible, like having these hackable features and having this increased expressivity and stuff like that. And that's the main reason why we didn't go for something like C#, because C# is kind of similar to C in that it's compiled in advance and so on typically, though you can do more stuff with C#, but it seemed better to have a language that is really different from C, so we really can take advantage of the dynamic features. Lua also has a popular language style, which is like, it's not too esoteric. It's not like Haskell or Lisp or other functional languages that require you to think in new ways. It's a pretty straightforward imperative style, something that it shares with other popular scripting languages such as Python, Ruby, and JavaScript. All these languages are very similar. They have some distinct features in terms of the syntax and how classes are set up and so on. But the feel of all these languages are very similar. I think it's appropriate to say that they all sort of belong to the same family of programming languages. And the reason why we choose in this family of popular languages, the reason we choose Lua instead of Python or Ruby or JavaScript is that Lua is smaller. It has smaller definition. It achieves the same thing as these other languages, but it has a much smaller definition, so it's easier to learn. It doesn't have these surprising edge cases. If you've seen the Watt presentation, you know that the Ruby and JavaScript are full of weird edge cases that sort of linger from behind, like what happens if you add an object and a number and strange stuff like that. And Lua is pretty clean from that kind of stuff. And it's very minimalistic. It's a very small language, both in the feature set that the language has, but also in the implementation is kind of small and understandable. And that makes it a really good language for embedding into another program. It's also well designed for extension, whereas Python and Ruby are sort of intended more to be used. They come with batteries included, so sort of ready set up libraries that do all possible kinds of things you can imagine, while as Lua just has a small language core, and then the intention is that you extend it to yourself by writing bindings to C functions that perform the actual functionality that you want. So it's more suitable for embedding an extension. It's very hackable because the source code is small. It's reasonable to look at, so you can play with it in various ways, which is something we really like. It also has a really amazing just-in-time compiler, Lua Yit, which is like probably the most performant just-in-time compiler for any of these languages, which is pretty amazing considering the amount of resources that are put into optimizing JavaScript Yits, for instance. So that's really a strong feature of Lua. A drawback of Lua Yit is that it's kind of lawyer limited in the way that we can not use it on all platforms, because some of the closed platforms like PS4 and Xbox One, they don't allow for just-in-time compilation of code. So we can't run a Git compiler on those platforms, which is unfortunate because it can give an order of magnitude speed improvement to running Lua code. But Lua has drawbacks too. It doesn't have any native multi-threading, which creates problems, as I talked about before in the threading talk. It doesn't have any static type system. It's all dynamically typed, which I think can be convenient for this. I think dynamic typing or duck typing can be convenient in this sort of exploratory phase when you're sort of exploring the design space and trying lots of different solutions. It's good to not be restrained by type system and having to add too much rigor to your code. But I think as your project sort of matures and start to accumulate more and more code, the lack of static typing becomes a bigger issue. Once you have like a 300,000 line project in Lua, or in any other of these dynamic languages like Python or Ruby or JavaScript, and you want to make some modification like rename a function or add some parameters to a function, the only way you can do that kind of refactors is basically just search and replace. And it's hard to know, did I find all the places? Did I fix all the things that I needed to fix, and so on? And a lot of proponents of these dynamic languages claim that, well, you should just have test cases that cover everything, and that won't be a problem. But I think it's quite hard, especially if you look at the big game projects with lots of gameplay code, really creating good test coverage for an entire system like that is pretty hard, I think. So and just having static typing and the sort of automatic refactoring that you can get from that in languages such as C# really simplifies those sort of refactoring operations and give you a lot more safety in performing them. So I do think that this is a big drawback, especially when your project gets larger. Another drawback of Lua is garbage collection. Shared with a lot of languages, of course. Garbage collection is not ideal in a game environment since it tends to introduce stalls. There are ways around that, but But usually in a game environment, it's better to have tighter control of your memory so that your memory is not growing out of control or stalling when you need to recycle it. So how do we work with Lua? How does Lua work with the main C++ code in the engine? Well, the first thing we need to do is we need to map between Lua types and Stingray types so that we can represent all the different kinds of types that we deal with in the engine in Lua, so that we can reason about them, do operations on them, call functions, and so on from Lua. So to see how we do that, we need to know a little bit about how types work in Lua. Lua has a small number of basic types. It has booleans, numbers, which are always doubles, strings, tables, which is used both for arrays and hashes or maps. These two things are sort of unified in Lua, which you could argue is maybe one of the not so good design decisions of Lua. But yeah, let's not get into those kinds of discussions, because you could argue either side for forever. And user data. So user data is something that is defined on the C side, and that's typically what we use to extend Lua with new types that are not covered by any of its existing types. So that's what we will use to represent things like cameras, units, lights, all the other stuff we have in the engine that we need to reason about from the script layer. So when it comes to user data, there are two kinds of user data in Lua. There is something called light user data, which is basically just a wrapped C pointer. So it's actually just a void pointer with no real other information for Lua than the pointer itself. So it doesn't tell you what kind of pointer it is, what it can do, and so on. It's just a way of wrapping a pointer in a type so that we can pass it around in Lua. Then there is something called full user data. It's sometimes just called user data, but I'll call it full user data to make the distinction between light user data and full user data more clear. So a full user data is a memory blob that we allocate, so a heap allocated chunk of memory where we can put whatever we like, whatever data we like to store. And together with garbage collection, so this heap allocated object is garbage collected just like any other data in Lua. So it will be automatically freed when there are no more references to it, but as long as there are references to it, it will continue to live on. And it also has a meta table. And a meta table is a table that sort of represents a type in Lua. So a meta table can contain, for instance, object methods. So object methods are functions that are stored in the table, in this table that is the meta table for a full user data object. So when a full user data object has a meta table, we can call methods directly on the object. So if we have an object here and we call do something on it with the colon syntax, which is Lua's way of calling methods, this name do something will be looked up in the meta table of this object, and we will find the appropriate function to call. So this is the way classes and types are implemented in Lua through meta tables. It's also used for implementing arithmetic operators and some other stuff. So full user data is kind of nicer because it gives us type information. We can look at the meta table to see what the type of the object is, and we can get this object calling syntax, this colon syntax, which is kind of nice. But it also has big problems from a performance perspective. Since all the full user data objects are allocated on the heap, it uses more memory. We need to allocate heap stuff. for each of these objects, and it also increases the garbage collection cost, because we get more objects that we need to go through when we do the garbage collection. And if you start to have a big game with lots and lots of objects, these costs can really add up. It's also more expensive, because when we want to go from the C object to the Lua object, we need to perform some kind of table lookup to see if this object has already been instantiated on the Lua side, if there already is an existing user data, an existing full user data representing this object. We want to use that. So we need to do a table lookup to find out if such an object already exists. We could use the alternative and create a new user data always, even if one already exists representing this C object. But then we get into kind of a messy situation where we have multiple different user data objects on the Lua side representing the same object on the C side. And it also leads to even more garbage collection, because now we will have not only one heap allocated object for each object that we represent on the C side, but we might even have multiple heap allocated objects in Lua representing the same object on the C side. So typically we want to do a table lookup so that we only have one full user data corresponding to each object on the C side. But then, of course, that table lookup is a bit expensive too. So for performance reasons, and performance reasons are really important to us. That's what engine development is all about. We can't really get into any crazy bad performance situations. So we really want to use light user data as much as possible. So we need to find some way of making that work. So let's go through the different problems we had with light user data and see how we can address them. So one problem is we don't have any garbage collection for light user data. So how does the data get freed? We handle that by having everything owned on the C side. So Lua won't actually own these objects, and they won't be automatically freed when they die, when sort of the reference goes out of scope in Lua. Instead, Lua will have to explicitly call a destroy operation in order to free it. So I talked a bit about this in the memory talk, that this is usually how we work. We don't use references to objects. Instead, we have strong ownership. So the application itself owns all the worlds where units can live, and the worlds owns the units that live there, and the units own the meshes that belong to the unit, and so on. So each object has a clear owner, and that owner controls the lifetime of the object. So when we want to destroy something, Lua will explicitly have to tell the owner to destroy that object. So either tell the world to destroy a particular unit, tell the application to destroy a particular world, and so on. This sort of strong ownership doesn't always work, because sometimes we have objects that sort of die automatically that we want to reference. For example, a sound lives for a short time, then it dies. And if we used a pointer, if you used like a hard pointer to that sound, then when the sound died and was deleted, we would get an access violation trying to use that pointer. So we can't really use that mechanism for these things that sort of die on their own. But for these things, we use some kind of ID system, and IDs are just numbers. So when we say play particle effect, we get an ID back. That's a number. And these numbers act as weak references. So we can ask the particle system, is this effect still playing, and pass in the ID. And the system will say either, oh, this ID is still playing, or no, this ID has stopped playing. So that way we can deal with these things that are more short-lived. So that's how we take care of ownership. The issue with method calls. Since we don't have a meta table, we can't call methods directly on object, because there is no type information for these light user data. So there is no way where we can look up what method it supports. And that means that instead of doing a call like this, do a method call, we have to do a function call like this. So we have to take the unit class, which is the class that store all the operations that we can perform on units, and we need to look up this method in that class and then explicitly pass in the object. So this is a bit more cumbersome to write than to write this directly, but it's not too bad, I think. It's not too much extra typing, and there are some good reasons for writing code like this anyway. As I said, we don't have static typing in Lua, which means that it is pretty unclear what kind of types objects have. And if we do the method call this way, we don't really have any information about what kind of object we have here, what kind of object the unit is here, that we call the method on. Whereas if we call it like this, we always know the type of the object because we're explicitly specifying it. This type of call syntax also allows us to cache the method lookup, which is sort of a micro optimization that you can do in Lua, so that we don't have to fetch the method from this table every time we do the call, which can be useful too. Of course, there might be situations where you need to do methods calls. For example, if you don't actually know the type of the object, if you want to do something where you dispatch to different, you have different kinds of objects that you pass in, and you do kind of a virtual call, so it dispatches to different functions. I don't think that kind of design is necessarily a very good design. It tends to lead to hard to understand code. But yeah, there might be situations where you want to do that, and in that case, you could, on the script side, you could wrap this in, not the full user data because you can't create that. On the script side, but you could wrap this in your own table with a custom meta table that sort of gives this behavior. So the script can sort of add the cost of a heap allocation in order to get this behavior in the specific instances when the script wants it. So you can get back that feature sort of in the cases where you really need it, and not have to pay the cost for it when you don't need it, which is kind of what we always strive for in the design of the engine. You pay for the features you want, but you don't pay a general cost for features that you don't need. So type checks. As I said, the light user data doesn't have any type information. It's just a void pointer, but we really want type information. For example, when the user calls a function like this and passes in an object, we want to check that the object is of the right type and give an error if the user passes in an object of the wrong type, and not just hard crash with an access violation or something like that. That would be pretty bad behavior, which would make it pretty horrible to program in Lua. So we want to do type checking, but how can we do type checking? We don't have any type information. We just have a void pointer. So we solve this by storing a type tag as the first member of all objects that we expose to Lua as light user data. So such an object, for example, the level object is such an object. It has as its first member a marker member, which is just an integer. And when we create a level, we store a unique marker value that specifies that the object stored at this address is of this type. We store that in this first member, and when we destroy the level, we make sure to clear this out. So this makes it possible to check if we have just a void pointer that comes from a light user data in Lua, and we want to know if it is a level. We can do a type check of that by just casting the pointer to an integer, and that's fine because we know this integer here is the first member, and we don't use multiple inheritance or something weird like that will mess with these pointers. So this pointer will actually point to the first member of the object, which will be this marker. So we can do a comparison and check that the marker is the marker this value that we expect for the level. Then we know that this pointer we got from Lua is a level. So this works for checking if you pass in an object of the wrong type. This check takes care of that. What if you pass in an object that has been destroyed? So what if you have a reference to a level in Lua, then you explicitly destroy that level, and after that you pass in that object to a Lua function. So if you use a light user data, pass it to the C side after it has been destroyed. Well, the most likely thing that will happen is that the type marker will no longer match, because it will have been cleared out by the destructor here, or it has been overwritten by some new object that has been created at this memory location and put some other random data into this marker. So most likely the marker will not match, and you will get a type error, and then you can sort of figure out what's going on and deal with it. There are other possibilities, like you could get an access violation if this memory, if this freed memory from this object if it wasn't reused, if it was actually freed all the way down to the OS layer, so we actually released the page that holds this memory, which is kind of unlikely because most of the time we reuse the memory for something else, but that could theoretically happen, and then you would get an access violation and a crash. You could also randomly happen to get a match, either because a new level object was created in exactly this place, or because some other object was created in this place and the bit pattern just randomly happened to match this level marker bit pattern. But both of these situations are kind of unlikely, and I think in this case, when we're sort of handling errors, it's not really super important that we always get this nice error message. If we get the good error message, which is the most likely case, if we get that 95% of the time or 99% of the time, then in most runs of the game we will get the good error message, and the user can fix the actual error. There might be a small chance that we get a bad error behavior, which makes it harder for the user to fix the error, but it might be that the user just runs the game again and then get the good error message. So I think this is a reasonable situation. It's not too terrible. So you can see this code, how this works in our Lua stack class, which is used to interface with Lua types from the engine. So it has methods for method for getting objects of specific types, and the implementation of that is specialized for each. Let's see if we can find type here. Yeah, it's specialized for each type into these check operations. So for example, we check if an object is a camera, we check that it's an object pointer, we cast it to an integer and compare it to the camera marker. And this here is an object pointer. It's used to distinguish this from unit and entity references, which I will talk about in a bit. So yeah, as I said, for units and entities, we have a special system, because for these objects, since they are so commonly used for gameplay elements, we want to be able to explicitly ask, is this unit still alive, or is this entity still alive, or has it been destroyed by someone else? So for since a raw void pointer doesn't allow us to ask that with confidence, it's okay when we do it for error handling. If it's an error, if it's already an error to use the object, it's fine if it sometimes, in rare occasions, causes an access violation. But if it's not an error, we're using the object, but where we have a sort of valid operation that we want to do, we want to ask, is this object still alive? And we consider that a valid question to ask, then it wouldn't be okay for this question, is this still alive, to sometimes cause an access violation. So in this case, we really need something that works 100% of the time. So for unit and entities, we have a weak reference system that allows us to do this query. And I talked a little bit about this before in the unit and entities talks. And the way it works is that we use the 2 lower bits of the light user data pointer to mark it as a reference. So if the 2 lower bits are 0, 0, then the light user data that we're looking at represents a regular void pointer. And actually we know that all our void pointers will have this bit pattern because our memory allocators align on 4 bytes automatically. So the 2 lower bits of the pointer will always be 0. So that's kind of nice. So that means we have sort of 2 bits of free storage here that we can use for other stuff. And we use it to mark unit and entity references. So if the 2 lower bits are 0, 1, then the light user data isn't a void pointer, it's actually a reference to an entity. And if it's 1, 0, no, to a unit, sorry. And if it's 1, 0, then it's a reference to an entity. And 1, 1, we don't use that pattern for anything right now, but we could use it for something in the future if we wanted to. And in these cases, where the light user data represents a reference, then the rest of the bits, the rest of the 30 bits represent an ID into the weak referencing system that we can use to query, is this particular unit still alive? And in that case, give me the pointer to that unit. And I talked about that system before, exactly how it maps to a unit, so I won't talk about that anymore here. Another interesting types of objects that create problems for us is linear algebra objects, like objects that we want to do math operations on. For example, vector 3. How can we represent a vector of 3 elements in Lua? Well, the best thing would be if we could represent it directly on the stack in Lua. So not do any kind of heap allocation or pointer reference, but it's just a stack allocated object, so sort of an immediate type instead of a reference type. But this is not possible in Lua. Only the native objects supported by Lua, double and string and so on, can be represented on the stack. We could extend that potentially to add more kinds of objects that has sort of direct stack storage. But if we want to increase the size of those objects beyond the size that is already used, which is 64 bits, which is used by a double or a light user data, which also can be stored here, that is a pretty big modification. That requires, if we want it to be sort of dynamically sized, all stack objects in Lua, that's a pretty big modification in Lua, and yeah, I don't even know how tricky it would be. It's not something we have even considered doing, because it's such an intrusive change to Lua and Lua JIT if you wanted to do that. So we can't represent them directly in place on the stack. We have to represent them by pointers somehow. So what are our options that way? We could use light user data, but that creates problems for us. For example, we can't do operator overloading like this, because operator overloading depends on meta tables. The multiplication and addition operators are looked up in the meta tables of the objects. So we can't write our arithmetic expressions in the most convenient way like this. Instead, we would have to write them something like this: vector 3 add vector 3 mul And you could argue that this is actually clearer than writing like this, but it's not that nice. When it comes to mathematical expressions, it's not too nice to look at them like this. But you could argue that we should write them like this anyway, and there are merits to that argument. But a worse issue with light user data is that we don't have any garbage collection. And these operations will create temporary objects. For example, when we create 2 times a here, we need to return the result of that. And if that result is that result will be a new temporary vector 3. And without garbage collection, which we don't have for light user data, who should destroy this temporary object? If no one destroys it, then we're leaking memory with every arithmetic operation, and that will create tons of memory leaks. So that doesn't really seem to work. What about full user data? Well, then we solve these 2 problems. We get meta tables, so we can do operator overload, and we have garbage collection, so we can garbage collect these temporary objects. But the problem here is that we will create a huge amount of these temporary objects. Like every single calculation we do will create like multiple temporary objects for all the intermediate results. So the amount of garbage we create will skyrocket, and we will get really inefficient systems with lots of allocations and lots of garbage collection. And this is so slow that it's not really acceptable. We could use tables, like we could use a table to represent the vector 3 and store the components in X, Y, and Z slots of the table. That doesn't really change anything. It's pretty much the same thing as a full user data. Tables are heap allocated too, and yeah, they have garbage collection and meta tables just as full user data. So it has all the same disadvantages as full user data. It might be slower or faster than full user data depending on whether you're in Lua or Lua JIT or whatever, but it has the same drawbacks. So none of these approaches seem to really work. So what do we do? Because of course we've made it work. We had to made it work. So our approach, our focus again, our perspective is always that performance is most important. We can't do something that really destroys performance. And that means we have to use light user data. We can't use full user data. So what to do about destruction? Well, requiring the user to explicitly destroy all the temporary objects that appear in a mathematical expression is not practical. That would be much too painful for the user. So instead what we do is that we destroy all the objects automatically at the end of a frame. So that means that no user destruction is required. We take care of that. We keep track of all the vector 3s that are allocated or created during a frame, and then at the end of the frame we destroy it. So this has some consequences for the programmer. It means that you can't save a vector 3 in a variable and use it in the next frame, because in that next frame we will have destroyed that variable. And so if you want to save it, you need to wrap it in something in order to get it heap allocated so that it actually lives on for multiple frames. So we have a special class for doing that called vector3 box that will take a vector3 object and sort of box it into an object that can live for multiple frames. So this is a bit error prone for the user. It's kind of easy to forget that. Usually we have, luckily we have systems for detecting that. So if you forget to wrap your vector 3 in a box and you use it in a later frame, you will actually get an error message from Lua saying that you're using a stale object. So in that case, you can go into your code and fix it. So it requires a bit of extra work from the user in order to box these objects properly. But that's the price we pay for getting decent performance for these arithmetic operations. The way we implement this system on the Onion side is that we allocate all these mathematical objects in reusable block buffers. So we have multiple big blocks of memory, and in these blocks of memory we store the data for these objects. So we store a type identifier. When we store a vector 3, we store a type identifier, and then we store x, y, and z components, and then we might store another temporary vector 3 here, and so on. And we also use this for matrices and quaternions and some other types. So we just store these temporary objects in big block buffers, and then the light user data just points to the type identifier here. So it works with the same marker system as we use for other light user data. We have a type identifier at the start of the object that the pointer points to. So the light user data will just point here for this vector 3, and here for the next vector 3, and so on. And each frame, when we get into a new frame, we recycle these objects by clearing out the type field and putting in a stale type marker instead. So the stale type marker will say, well, this is a vector 3, but it was created by a previous frame, which means that if you try to use it, you will get an error. Of course, the buffer might eventually wrap around and overwrite this information. So if you haven't used it for a long time, you may get a worse error. But this is again one of those situations where most of the time you will get the good error message, which is usually good enough in this case. So operator overloading is the other thing we wanted. So being able to write expressions like this using vectors is kind of nice. And we actually can implement that. So although we can't have meta tables for individual light user data, so we can't assign a specific meta table to a specific light user data object, what we can do in Lua is we can use a single meta table for all light user data. So we can specify one meta table and say that all light user data, no matter what type it is, because light user data doesn't have type, but all light user data should use this meta table. And then in that meta table, we can implement these operator overloads, and the implementation here can check the type of these objects, of the involved objects. Is it a vector 3? Is it a vector 4? And so on, and call the appropriate function for doing the multiplication, the addition, and so on. And this adds a bit of extra type checks and branches to the implementation of these operators, but it's not super expensive, and in a lot of cases it's worth it in order to be able to use this simpler expression style. And you can always use explicit calls if you really need to. And the implementation of this is in the Lua environment classes. So for creating a temp vector tree, there are functions for doing that. It will allocate memory from these buffers, from these block buffer, like just blocks of memory, and then it will cast that into a temp vector 3 object, which is basically just the vector 3 with this type marker in front of it, and then return it so that it can be used. And in the CPP file, we have the corresponding. Let's see. We have this corresponding code for clearing out these stale values. So it goes through all the temp variables that were created since the last call here and changes their marker into this stale marker, which will give an appropriate error if the user tries to use the object later. So that's the implementation. One problem with this is that we only free this memory at the end of the frame. So if you use a lot of linear algebra, these buffers will grow and grow and grow. Like if you do 200,000 multiplications, you will allocate 200,000 temporary objects. So the buffers can grow very big. We have a mechanism for dealing with that. So if you know you're about to do a lot of temporary arithmetic operations, you can save the current size of the buffer, the current amount of used temporary variable memory. Then you can do all these computations that you want to do that will generate a lot of extra memory. Box the results that you want to keep so that you preserve them, and then reset the buffer size to whatever it was before you started these temporary computations. So that will free all the memory from all the temporary intermediate results that were generated during these computations. So we do have a mechanism for controlling the growth of these buffers in the cases where you need to do that. But most of the time you don't have to worry. It's just if you have very specific systems that do a lot of computations, you might want to look into this. So Lua bindings. By bindings we mean the way we call C functions from within Lua. I've gone through how we map types, so how the C types are mapped to the Lua side, but we also need to map the functions themselves. So Lua uses sort of an abstract stack for passing parameters and return values. So the callback functions that are called from Lua always take a Lua state as a single parameter and returns a number, which is the number of return values by this function. And to get the parameters of the function, you call various functions like Lua toNumber to convert the eth parameter, so the first or second or third parameter, to this function to a number. And you get an error if it's not the number, and so on. And then you have similar functions for accessing string parameters, Lua toString, and so on, that do the same thing. And to return values, you push them on the stack. So you do corresponding Lua push number and push some number x that is the result of your computation. And then you return 1 to indicate that you have created one value. You could push more values because Lua functions can have multiple return values. So we need to make sure that we can go from this to a C function call, which is what we need to call on the engine side. So there are a number of different ways of doing that. You can do manual bindings, which means that you write these functions yourself, all these wrapping functions. So for each function that you have on the C side that you want to expose to the Lua side, you would write a function. For example, if you want to expose world spawn unit, you would write a function world spawn unit Lua state, and then it would extract the arguments like get world pointer and so on, and then call the corresponding C function, push the return values and return. If you don't want to do manual bindings, there are other options. You could do automatic code generation from the header file. So you write a program that parses the header file and outputs functions like this. You could do some template magic, where you have template magic that sort of unpacks the argument of the function, that figures that out through template matching and then calls the corresponding stuff. Or you could do foreign function interface, where you put the stuff directly on the C stack the way C wants it, through assembly language or low code hacking, and then jump directly to the C function to perform it. Of these options, we've decided to use manual bindings, and the reason we do that is that we want to have detailed control over what the Lua API look like. When you have these the template magic stuff, that's really slow to compile, and it's really greasy, hard to debug, and pretty awful overall, I think. Code generation 2 is not so nice. Then you have all these lots of auto-generated code in your engine, and if you want to do something special, that becomes really hard, because then you have to insert special markers and then modify your code generation stuff so that it handles that case specially, and so on. And we also want to do proper error handling, which means that we don't just want to call our C functions. We want to check that the parameters are good, that they have decent ranges, that they have the right types, and so on. And frankly, writing the manual bindings is not much work. It's a couple of lines of code for each function that we want to wrap. So I think the sort of cost of doing, the benefits of doing manual binding outweigh the costs of doing that. But you could argue that since we now have this C API, an API for calling everything to C, and since now the Lua API is built directly on top of the C API and should look the same as the C API, we could go to a more automatic method of generating these binding functions, since they now have a strict C interface that they should always call. Not sure if it's worth going to that. It might be, but as I said, it's not too much work to write these Lua functions, and you need to write documentation for them anyway. So you need to do the work anyway. So just as an example of how this might look, this is the binding for our units. So let's find some function here. Yeah, here's an example that binds the local position function for fetching the local position of a certain node in the unit. And this is actually the Lua function that will be called. We're taking advantage of the lambda syntax in C++11 to not have to sort of write this function inline instead of writing it in a separate place, which makes the code kind of harder to follow. So this uses our abstraction of the Lua stack. This is our own class that abstracts the Lua stack and makes it a bit easier to work with it. To get it has functions for checking the types of items on the stack, getting items of a specific type from the stack, of all the different types that we support, doing this light user data mapping of objects and pushing objects and so on. So it's just an abstraction that we have over the Lua stack for dealing with the types we have in our engine. So it extracts a unit reference, which is the first argument here. It extracts an index of the node, and then it calls the local position in the plugin C API to get the vector 3 of that indexed object, and it pushes that to the Lua stack and returns 1 since we've generated one value. And this is pretty much how all these wrapper functions look. They get parameters, do some error checking, and then they call into the C API and push the results and return the number of arguments. So it's very straightforward code. We also do documentation of the Lua functions directly in the code. This documentation is parsed using our own system called ADoc, which parses the sort of Lua signature and arguments. It's a bit similar to Doxygen, but adapted for working with Lua. So this is what actually generates the Lua API documentation that you can find on the Stingray website. Yes. So we also have support for hot reloading in Lua. and it works through the refresh call, as I talked about when I talked about our resource management. So it works the same way as other resources. The user does refresh, we get the list of resources that have changed, and if any Lua resources have changed, the way we handle that is that we just run the code again. And this might be a bit non-obvious, but running Lua code again will actually update the Lua code. When you have a function definition in Lua, it will look something like this. You have a function added to some table here to draw an object, and then you have some implementation of that function and so on. In Lua, this function definition is just syntactic sugar for this, for taking the table object, assigning the draw field of the table object to a function that gets as first parameter the object itself. That's because we use the colon syntax here, which means that it's an object method, and then the size, and then comes here the actual code that does something, and so on. So if we change the Lua files, we change the definition inside here and run it again, what will happen is that this assignment will run again, and this assignment will just update the draw function in this table. So it will create a new draw function and store it in the table, which means that we've changed the implementation of the draw function. So actually, all we need to do to hot reload Lua code is just to run it again, and it will update the function definitions. Some care must be taken with class definitions. Typically, if you create a class like this in your Lua code, when we create this table to represent this class and hold these functions, if we just do like this, we create a new empty table and make this class be this new empty table. This creates problems when we reload, because if we run this code again, what will happen is that we will create a new table and then set the shape reference here, the shape class, to point to this new table. But all the old shape objects that we've already created, they will still use the old shape class as their meta table. And when we get to the function definitions later, since we created a new object here, these assignments won't update the functions in the old class. They will actually set the functions in this new object that we created. So all the old instances of this class will still use the old code. And that's typically not what we want. We want a reload system where we can reload the code and all the old objects also get the new behavior. But we can do that quite easily by changing the creation of this class to a syntax like this. So we assign the class to be either the class itself or an empty class. This means that the first time this is run, we create a new empty object, and that becomes the shape class. But if we reload the code, this will have a value. So the shape class, we will not create a new object for the shape class. Instead, we will continue to use the existing shape class. And then when we get to these function definitions, they will just update the function references in this existing shape class. And we have a standard sort of class implementation in Lua. Lua doesn't come with its own class and object definitions. You have to create them yourself in Lua, but it's kind of easy to do with the tools that Lua give you. So our standard class implementation already takes care of this. You write a class, you create a class like this, and then it will automatically reuse the existing class on reload. Garbage collection in Lua. As I said, garbage collection stalls are really terrible for real-time projects. Stalls of any kind are really unacceptable for real-time projects. You don't want your game to freeze for multiple seconds or minutes or whatever it may take to perform a full garbage collection cycle. Luckily, both Lua and Lua Types supports incremental garbage collection, so we can garbage collect for a certain number of milliseconds every frame. So instead of waiting until we sort of hit some memory limit and then do full garbage collection, we can garbage collect a little every frame. Now, one tricky problem here is what x should be in this case. How many milliseconds should we spend on garbage collection each frame? The incremental garbage collection in Lua is an incremental mark and sweep. What that means is that it will go through all the objects that we have in the game, that we have in Lua, go through all their references, mark all those references as being used, and then go through each of those objects, mark all the objects that they reference as being used, and so on and so on and so on, until it has marked all the objects that are currently in use. Then it will do a sweep phase where it goes through all the objects that exist in Lua, and every object that is not marked as used will be freed, will be garbage collected. And an incremental mark and sweep means that it does a little piece of this work every time. So it doesn't do the full mark and the full sweep in one go, which would create a huge stall. Instead, it does a little bit of marking work, a little bit of marking work, a little bit of marking work every frame, and then it gets to the sweep phase and does a little bit of sweeping work, a little bit of sweeping work, and so on until it has completed the cycle. And the tricky thing here is we don't really know how big the space of objects that we're sweeping is, so we don't know how much work we have left to do until it's done. So we don't really know how much time we should spend on this. It's not until we actually get to the end of the sweep phase that we know how much garbage we had, how much of these objects that were actually not used. And if we do too much garbage collection, then we're essentially wasting time for no good reason. We're wasting milliseconds, which are a precious resource in any game, and not getting anything out of it. And if we do too little garbage collection, then we won't be able to keep up with the amount of garbage that the game generates, which means that the game will eventually run out of memory because it creates more garbage than we are able to sweep up. So how do we deal with this? Well, we actually kind of treat this as a control problem. We have a knob that we can twist, which is the amount of milliseconds that we spend sweeping, and then we have some output variables, which is the amount of garbage we have, which we can sort of estimate because we know the amount of memory that weren't garbage from the last sweep we performed. Like when that sweep ended, we know how much memory we had that was not garbage. So we know the total amount of memory because we can keep track of that. We can keep track of all allocations. So we can sort of estimate how much garbage we have. So what we do is we sort of scale the collection time based on our estimation of how much garbage we have. So if there seems to be a lot of garbage, we scale up the collection time, and it seems there's not so much garbage, we scale down the collection time. So this is very like touchy-feely kind of stuff. It's not 100% guaranteed that it will work, but it seems to work well in practice. We've released multiple games on the engine with this method, so it seems to work well enough in practice. But this is the code that does this. It sort of tries to measure the amount of garbage we have. Then it lerps the amount of time we should spend collecting between a minimum collection time and a maximum collection time based on how much garbage we have measured. And then it loops until that time has passed and performs incremental garbage collection steps. And these different parameters are exposed, so they can be tweaked for a particular game. So if you need more garbage collection for particular game, you can sort of tweak these minimum and maximum times and the amount of acceptable garbage and so on. An interesting thing with garbage collection is that you could run it on a background thread. If you know that none of the other threads are touching Lua at the moment, then you can do garbage collection in parallel on any other background thread. As long as you only have one thread touching Lua, it doesn't matter what core that thread lives on. But currently we don't do that. We run the garbage collection sort of serially, but it's definitely something that could be used in the future. Of course, it runs serial together with the job system, so it still will run in parallel with render jobs, for instance, but it could be made more parallel. Another thing worth mentioning is our custom Lua allocator. So we need a custom allocator because Lua JIT, when it runs on a 64-bit system, can still only address the lower 2 gigabytes of memory. And that's because Lua JIT wants to use an efficient way of storing the pointers. So it actually uses nans to store the pointers and sort of store them in the double values, and that can leads to a lot of performance benefits on the Lua JIT side. But it's kind of annoying that Lua JIT cannot represent all the possible pointers that can exist in a 64-bit allocation or in a 64-bit application. So we need to deal with this somehow. What we could do, we could allocate the entire 2 gigabyte range at the start of the program and give it to Lua JIT. But there are two problems with that. First, it uses a lot of memory. We don't want to allocate 2 gigabytes at the start of the application. Also, we don't know if that whole range is available. It might be that some of that range is already used by DLLs or by the application code itself and other stuff, so it might not be accessible to us. So we have a special system for dealing with this, which is called the low address page allocator, because it tries to address it tries to allocate virtual memory pages, but only in this low address space, the lower 2 gigabytes. The first thing it does is that when it starts up, it reserves all this memory, but it does not allocate it. So it reserves the address ranges, the address space, but does not actually physically allocate the memory. So we don't get the 2 gigabyte memory use. And the way we deal with the fact that the entire range might not be available is that we sort of do a divide and conquer algorithm. So we try to allocate the entire 2 gigabyte address range first. If that fails, if we can't get that because some other system is already using part of that address range, we split it in half and then we try to allocate both halves. And if we fail with one of those, we split it again and allocate those halves. So, and we continue that up to like, I think we stop at like 2 megabyte chunks. So this is a pretty efficient way of allocating as much address space as we can within this address range. And then we use a body allocator structure to store this memory. It's basically a way of representing allocated memory that's being split up in this way. It's always splits in half. The blocks always split in half. And then we create a heap for Lua, a regular heap, a regular DL-malloc heap that uses this body allocator as its backing allocator. So whenever the heap needs more memory, it will get it from these reserved pages that has been reserved by this allocator. We support debugging of Lua too. The implementation of that is quite simple. We have a WebSocket interface similar to our other WebSocket interfaces that takes debugging commands for breaking, stepping, evaluating, and so on. And these commands just get turned into the corresponding Lua debugging commands which exist in the Lua API for performing these operations. And if there are any results to be returned, for example, from the eval command, these are returned by other WebSocket messages that send the result of the eval operation. So that pretty much covers everything I wanted to say about Lua. Are there any questions on this?
Do we know what's going to happen with Lua? Because there was some question about whether Mike Paul would continue maintaining it in the future or not.
Yeah, I'm not sure exactly. I haven't been following that lately. I know Mike Paul stepped away from Lua Yet, but then I saw he was active on the Lua Yet. He was back being active on the Lua Yet mailing lists again. So I'm not completely sure actually what the current status is.
Okay.
Anything else? All right. Talk to you tomorrow again. Thank you.